Hi everyone, this is Professor H. Rahman from Agricultural and Food Engineering Department, IIT Kharagpur. I welcome you all to this NPTEL course on traction engineering. This is lecture 14 where I will try to cover tractive effort and slip of a powered rigid wheel. When I said it is a powered rigid wheel, that means a rigid wheel which is powered, which is moving at an angular speed omega. So, the concepts which will be covered will be your slip and tractive effort. So, if you look at this figure in the left corner, I have shown a powered wheel with a rolling radius r, and it is moving with an angular speed omega, and b is the actual speed which I have indicated here. So, since it is powered, that means it will be developing a shear force along the shear stress along the contact area. This is the contact area where you can develop the shear stress because of the interaction between wheel and soil. Now, if you want to develop tractive force which is developed by the rigid wheel, then we need to know what is the shear stress developed, and shear stress is a function of shear displacement. So, we have to find out what is the shear displacement at the contact area, then only you can find out what is the shear stress developed, and shear stress into the contact area. So, that will give you the thrust or the tractive effort which is developed by a rigid wheel. So, shear displacement which is developed along the contact area of a rigid wheel will be decided based on this analysis of slip velocity. When I said slip velocity, that means difference between theoretical speed and actual speed. Both are in the same plane, then only you can find out the difference, and then that is denoted as Vj. Now, if you consider that wheel is rolling, so theta 0 represents the angle at which the wheel is in touch with the soil. This is called entry angle, and we will now consider a point say A, which is making an angle theta with the vertical. So, at A, the peripheral speed will be equal to omega r. Omega is the angular speed, r is the rolling radius. So, peripheral speed will be omega r, and this will be equal to your Vt, which is theoretical speed. Now, at this point the actual velocity is given as v. Now, if you resolve this into this plane, so this angle will be equal to how much? Theta. So, v if is resolved in this plane, then it becomes v cos theta. So, now Vt minus v cos theta will be equal to your slip velocity Vj. So, in other words, you can say slip velocity is nothing but the tangential component of the absolute velocity at any particular point where you are interested in finding out the slip velocity. Okay. So, now Vj will be equal to Vt minus v cos theta. Now, if I substitute v in by I in the sense we know slip velocity is nothing but 1 minus v by bt slip, where I is the slip, b is the actual velocity, and Vt is the theoretical velocity. So, from here we can find out v will be equal to 1 minus I into Vt. Okay. Now, if I substitute for v in this equation number 1, so then Vj will be equal to Vt minus 1 minus I into Vt. Now Vt will be equal to Vj will be equal to Vt minus 1 minus I into Vt. If I take Vt common, so then it becomes 1 minus I. Oh, this is Vt cos theta. Okay. Now and Vt is nothing but omega r. This is the theoretical speed. Now omega r. So finally Bj it can be written as 1 minus I. I is the sleep and cos theta. So if you look at this equation now, the sleep velocity is a function of angular speed, is a function of rolling radius, is a function of angle theta, and is a function of sleep. That means for a given wheel and given operating condition, that means where the angular speed is given, then sleep velocity is a function of theta and sleep. Now from the sleep velocity you have to find out what is the shear displacement. Shear displacement which is occurring at the contact area. So if J is the shear displacement along the wheel soil interface, then J can be written as J is the shear displacement. Then this can be written as Vj into dt. So if you want to find out for the entire contact area, then this has to be integrated from say theta to theta 0 if I am considering from point A. Okay. Now Vj we can write as Vj is nothing but your omega r into 1 minus I into cos theta into dt. Now theta is equal to omega t. So d theta by dt will be equal to omega. Now you substitute for dt here, so that means dt will be equal to d theta by omega. So now substitute for dt. So this equation becomes omega r into 1 minus I cos theta into d theta by omega. So this omega will cancel out. So now what I get is theta to theta e. Now r into 1 minus I cos theta d theta. So this has to be integrated from theta to theta e. So that means the final expression will be r into theta 0 minus theta 0 here, theta 0 minus theta 1 minus I sin theta 0 sin theta. This will be the final expression for displacement. So theta 0 is the entry angle and theta is the point at which you have considered. Now knowing shear displacement, the next question is what is the relationship between shear stress and shear displacement. In nature, from the experimental observations, what we observed is there are three relationships normally existing. So let me show those relationships between shear stress and shear displacement. So, in case of a loose sand or saturated clay or most of the disturbed soil, the relationship between shear stress and shear displacement is tau is equal to tau max into 1 minus e to the power minus j upon k, and where tau max is written as C plus sigma tan phi. Sigma is the normal pressure. Sigma C plus sigma tan phi into 1 minus e to the power minus j upon k, where j is the shear displacement and k is the shear deformation modulus. Now, for organic terrain, the relationship between shear stress and shear displacement is tau is equal to tau max into j by kw into e to the power 1 minus j by kw, where kw is the shear displacement where the maximum shear stress occurs. Now, if it is a compact sand or silt and loam, then the relationship is tau is equal to tau max into kr into 1 plus 1 upon kr into 1 minus 1 upon e minus 1 e to the power 1 minus j by kw into 1 minus e minus j by kw, where kr is the ratio of residual stress to the maximum shear stress and tau max, and kw is the shear displacement where the maximum shear stress occurs. You can choose any one of these equations and then find out the shear force which is acting. Once you know the shear stress, then we will find out what is the shear force acting. So, shear stress will be, suppose for example, we take shear displacement in loose sand or in most of the disturbed soil, that is the relationship is tau is equal to tau max into 1 minus e to the power minus j upon k. If I take this relationship, then the equation will be, so shear stress distribution will be like tau max into 1 minus e to the power minus j upon k. So, tau max can be written as C plus sigma tan phi, where C is the cohesion, phi is the angle of internal friction, and sigma is the normal stress. So, j by k. Now, we have the expression for j. So if I substitute there, then C plus sigma tan phi. Sigma means you can write as sigma distribution of sigma along the contact area, sigma theta into 1 minus e to the power minus j. So, in place of j, I can write r by k into theta 0 minus theta minus 1 minus I into sin theta 0 minus sin theta. This is the distribution of shear stress. Now, in a rigid wheel, what you are interested in developing is the thrust force. So, now the shear stress, suppose this is the soil surface, okay. Now, the stress which is developed, from there we will find out what is the shear force which is acting. Shear force will be like this. So, shear force will be equal to the shear stress into area. So, I can write shear stress, shear force will be equal to tau theta into, if you take a small element here, then elemental area will be dA, and dA will be nothing but, if B is the width of the wheel and that small element is subtending an angle d theta. So, dA will be equal to r d theta into B. So, tau into B r d theta or B r tau theta into d theta. So, this will be the shear force. Now, for finding out tractive force, you have to resolve into two components. One is the horizontal component. This horizontal component is denoted as tractive effort. Okay. So, tractive effort will be denoted as F will be equal to this shear force which you got, cos component of that one. Okay. So, tau theta BR tau theta into cos theta d theta. So, this has to be integrated from 0 to theta e. So, this becomes a tractive effort. Now, while evaluating the performance of a powered rigid wheel, we have to find out, in addition to tractive effort, other parameters like what is the drawbar pull, okay, then what is the weight, the expression for weight, and then you can find out what is the wheel torque. And of course, we can find out other forces like coefficient of traction and coefficient of gross traction, CGT. So, for finding out pull, then we have to find out what is the rolling resistance. Okay. So, if you know thrust minus rolling resistance will give you the drawbar pull. Now, because of the weight, there will be Saul reaction. The radial force will be acting, and it will have two components. Okay. So, this horizontal component of radial force, this is radial force. The horizontal component of radial force will be equal to your rolling resistance. So, first we have to calculate the vertical component. One vertical component is from the shear force, the other vertical component is from the radial force. So, summation of that will give you what is the weight. So, weight will be equal to RB, this has to be integrated from 0 to theta e, then P theta or sigma theta into cos theta d theta plus 0 to theta e tau theta sin theta d theta. Now, for drawbar pull, this will be equal to P, and this is tractive effort, which is nothing but RB 0 to theta e tau theta cos theta d theta minus sigma theta sin theta d theta. This has to integrate from 0 to theta e. So, this will be the expression for P, this will be the expression for W, and for the wheel torque, if you know the tractive effort, then tractive effort multiplied with the rolling radius. So, that will give you the wheel torque. So, tractive effort is your thrust force is RB 0 raised to the theta e tau theta d theta into R. So, this R I will take out. So, it becomes R square B d theta. So, these are the expressions which you can calculate. The only thing which we need to know is what is the distribution of shear stress, what is the distribution of the normal stress. Then only you can find out the shear force, then what is the pull which is developed, what is the vertical load which is acting. Now, Wang, scientist, he found out the shear stress and normal stress distribution, and he measured and derived from this formula, and then what he observed is a very interesting thing. Interesting in the sense, this is the measured and predicted shear stress and normal stress in compacted sand at a slip of 22.1%. If you look at this figure, then the procedure which we followed for finding out shear stress and normal stress distribution along the contact area is quite close, we can say. Measured and the predicted values are quite close. Hence, the procedure which we followed is all right. So, in this lecture, attempts are made to derive equations for predicting tractive effort for a powered rigid wheel, and that the important components are the shear displacement, and we have derived expression for slip velocity, and slip velocity from here we try to find out what is the shear displacement, and knowing the shear displacement and shear stress relationship, we can establish what is the shear stress which is prevailing in the contact area. Now, knowing the shear stress, then we try to multiply the contact area so that we can find out what is the tractive effort developed. So, you can refer to the books like the Theory of Ground Vehicles by Wang J.Y. and Solid Dynamics Intelligent Traction by William R. Gill and G. Vandenberg. Thank you.